All right, good morning. We're going to look at some 5-4 problems, recognizing that we can use a table of indefinite integrals to help us out along the way. First, we need to verify this is true by differentiation. So if I differentiate the left-hand side, take a derivative, I would end up with just what's on the inside. So when I differentiate the right-hand side, I want to make sure I get that quantity that's inside the integral. Good, so let's do that. So on the right-hand side, I'm just going to take a derivative of this. So the derivative of the top, I might rewrite this as 1 plus x squared to the 1/2 over x. And let's just use, I guess we'll use the quotient rule. So the derivative of the top to the negative 1/2, you get a chain rule out of that, times 2x times the bottom, subtract off the derivative of the bottom, which is just 1, times the top, which is negative, makes me a plus 1 plus squared. And I could say that I chose the negative to go at the top. I could have put it anywhere I wanted, really. All that divided by the denominator squared. Now I just need to simplify that and verify that I get what I had before. So notice this. Cancel with that 2. And then if I multiply through here by, let's just say x to the 1/2, top and bottom. 1 plus x squared to the 1/2, top and bottom. That's going to simplify very nicely for us. So I'd have 1 plus x squared up top. Oh, excuse me. I have 1 up top times x squared. Right there's my x squared. So we'll just call it x squared. And there's a negative along with it, plus, and then I'd have 1 plus x squared. All that over x squared times 1 plus x squared to the 1/2. That and that go away, and I end up with what I had inside of the integral. We need to verify, again, the same thing, so let's just do that. So let's take a derivative of the right-hand side, take a derivative with respect to x of that, and I get sine of x goes to cosine of x minus, so then here we're going to have the 1/3, the 3 is going to come down, we're going to have sine squared x times the derivative of what's inside, which is cosine x. Factor out the cosine of x, and then I'd have 1 minus sine squared x, but 1 minus sine squared x is just cosine squared. So that gives me cosine cubed, which is what we wanted. Find the general indefinite integral. This is a great opportunity to think about that table. And looking at this table, we see that we have x to some number, which is the x to the n. We have that little pattern. And then we also have, move out of the way, a negative 2. So let's just do that. So the first one here, this would be equal to x cubed over 3 plus x to the negative 1 over negative 1 plus a constant. And you can simplify that if you want, but we'll leave it there. All right, likewise this one. This right here is like to the 3/2. So this would be, you could rewrite it if that's easier, x to the 3/2 plus x to the 2/3. So what happens? The numerator goes up by 1. And then I divide by that. But with fractions, I sometimes just flip it over. Since dividing, it's like multiplying by the reciprocal. I could go up 1 and multiply by the reciprocal plus a constant. There you go. 11 must be the same question, just what is this equal to? Let's simplify it up a little bit. That'd be x squared minus 2x to the negative a half dx. So x cubed over 3 minus 2x to the 1/2 times 1 over 1/2, or times the reciprocal, so this makes that 2 and 2 of 4. Plus an arbitrary constant. This one, maybe it's a little bit weirder. What was cosecant squared? Let's look at our table. That's right in there. Cosecant squared was negative cotangent x. So this is negative cotangent, in this case t, because it's giving me a t instead of an x. And then minus 2e to the t. Those don't change. Plus an arbitrary constant. All right, now look at the difference between this one and the one before. We've now been given bounds, so we need to evaluate this definite integral. The first step is going to be the same. We're going to do, that's x cubed over 3 minus 3x. The arbitrary constant doesn't matter here because we're going to evaluate it at 3 and negative 2. So when I'm going to plug in the 3's, that's going to give me 3 cubed, which is 27 over 3 minus 9. So that's when I plug in the 3. And subtract off plugging in the negative 2. So negative 8/3 plus 6. Make sure you get everything in the right order. 27 thirds is just 9 minus 9, so that's 0. So in this case, it's really just 8/3 minus 6, which if we want to put it in the same terms, which should be 18/3, that'd be negative 10/3. Got another one here for us. 1 goes to, well, and look, in this case, instead of x, we've got a w, so 1 just goes to w plus, well, this is going to be w cubed over 3, but the divided by 3 into 6, which is going to give me a 2. So you can verify that. Minus, for the same reason, w to the 5. And we need to evaluate this at 0 and 3. When I plug in the 3, so I'm going to have 3 plus 2 times 27, which is 54, minus 2 times, oh my gosh, 27 times 9. I'm just going to stick this one in the calculator. 3 to the 5th times 2, which is 486. And then we have to subtract off from that. 0 is plugged in, but those are all just going to 0. So in the end, I get negative 429, according to my calculations. For a problem like this one, we might write this as 4 u to the negative 1/2 plus 6 u to the 1/2, still inside of my integral. So this would be 8 u to the 1/2 plus, I'm thinking here, this would have been u to the 3/2. That 3/2 would have come down, so that would be a 4 right there, because 4 times 3/2 gives me 6. Now, because we're doing definite integral, we don't need the arbitrary constant, so we're going to plug in 4 and 1. So 8 times, what's the square root of 4? That is 2. Plus 4 times, well, the square root of 4 is 2, and then we cube that, so times 8, and subtract off from that 8 plus 4. So this, doing a little bit of math magic, is 16, right? Multiplying by 2, that's my math magic. That's all you're going to get today. Plus 32 minus 12, which looks to be about 36. Here's another one for us. 5 halves x squared. And you say, ooh, 5 to the x. That one's a little bit different. Why don't we go ahead and look at our table? We have a constant to an exponent. When you take the integral, remember when we took a derivative, we hit it with a natural log. Now we're going to divide it by a natural log and go the other way. So this would be minus 5 to the x over natural log of 5. I've got a 0 and a 1. We're going to evaluate that at. So when I plug in the 1, I just get 5 halves minus 5 over natural log of 5. I'm going to subtract off of that. Sorry, my stomach's all rumbly right now. I don't know if you can hear that. The zeros, which would be 0 minus 1 over natural log of 5. So that'd be minus is plus. So it depends how far you want to go with this one. This would be 5 halves minus 4 over natural log of 5. Call that a day. Um, 35 is very similar, right, for this one. It's just x to the 11 over 11 plus 10 to the x over natural log of 10. 0 and 1. 1/11 plus 10 over natural log of 10 minus the zeros, and you can simplify that. Now this one, you're like, ooh, that's a bit nar. Let's simplify it a little bit before we integrate. So that would be, well, there's two ways we could decide to simplify this. One, we could look for, hey, what about 1 over cosine squared theta plus 1 d theta. And I'm looking at my table and say, oh, is that on here? I don't quite see it written like that, but then I say, wait a minute, cosine squared in the denominator, that's secant squared. Right, this is the same as 0 to pi fourths secant squared theta plus 1 d theta. And for secant squared, that goes to tangent theta. I have that in my table. Plus theta. I'm using theta here instead of x. And we're going to evaluate that at 0 and pi fourths. All right, so when I plug in the pi fourths, tangent of pi fourths is 1. Theta is just pi fourths. And I subtract off zeros. So tangent is sine over cosine. When I plug into 0, I get 0. And likewise, I get 0 for theta. So it's just 1 plus pi fourths. And I think that is all for the 5-4 homework, so hopefully this helps. I could explain some of these more, but as a resource for you, just want you to be able to see someone work these out with alacrity.